one remark about this exponential decay here. It's also as a consequence of assumptions 1 and 2, it defines a norm. So if we define xs equals to mu x hat dot x, this defines a norm on RD. And actually, I want to divide by m of E1 just to normalize it. So this defines a norm on RD. So it's, the triangle inequality is relatively easy to verify just using the optimality of this mu x hat. And it's always the case that it's in between the L1 norm and the infinity norm, the other way around, the infinity. Thanks to that normalization I put in. So that means that it's possible to rewrite this exponential decay here as m of E1, which was, you know, the edge of omega there on the axis, times this norm of S, like we saw in the Yoffe theorem for self-avoiding walk. So that's nice. And actually, the fact that this mu x hat is defined via this optimization problem, you can use Lagrange multipliers to compute what this norm is in some situations. I'll tell you what it is in one situation shortly. That's an interesting fact, but it's a bit of an aside for the crossover theorem. So in the crossover theorem, what I want to say next is that this Brownian green function it's explicit. You can just write it down. So explicit. You know, thank goodness for integral tables. So Cx, if we look at it in the direction, I'll emphasize that this eta is in the direction of x. This thing is just equal to 2 over 2 pi to the d over 2, 1 over the square root of the determinant of lambda. The L2 norm of eta divided by the L2 norm of x to the power nu. Modified Bessel function of the second kind, evaluated at w squared. I have to tell you what some of these things are. Like that. E to the w squared, a to 2 x2, where nu is d minus 2 over 2. K nu is the modified Bessel function of the second kind. And w squared is x hat lambda inverse x hat. So it's a bit of a mouthful, but it's explicit. And everything is known about the Bessel function. And so we know everything. We know everything about this amplitude here in the asymptotic formula for S. So what about this K nu? It's very explicit in the case of d equals 3 or d equals 1. You can write it down. It's a simple function. I mean, it's an easy elementary function involving exponentials. In general, these Ks, unlike the modified Bessel functions of the first kind, diverge at 0 and decay exponentially. This factor is just canceling the exponential decay of the Bessel function, so that what remains is a power law. So this is a power law. So, you know, you've got a bit of looking into the Bessel function in order to figure out what's going on there, but known properties of K nu, you just look them up, imply precise asymptotics or S depending on what regime you're looking at. Whether you're looking near the critical point when eta goes to 0 faster than the correlation length, or like the, so let me just write down what the formula is. So for example, Cx, eta x hat, is bounded above and below by the norm of eta max x inverse to the power d minus 3 over 2 divided by x to the d minus 1 over 2. And this holds uniformly in X, in non-zero X, and in eta, or d greater than 2. So remember that eta has the size of the mass. That was one of the statements in the proposition, that the norm of eta was comparable to the mass. So you just think that if we had a parameter in the model so that the mass was going to 0, then this eta would be going to 0. Okay. So as a corollary, S of x is going to be bounded above and below by the mass, or that divided by x to the d minus 1 over 2. So once x is much bigger than the correlation length, that means that this alternative will be the one that achieves the maximum. Sorry, if x is of the order of the correlation length, if these two things are comparable, then you can take x, here. These two powers will add up to d minus 2. So if x is, of the same order as m, this is 1 over x to the d minus 1 over 2. On the other hand, if x is much greater than m, then this is m to the d minus 3 over 2 divided by x to the d minus 1 over 2. So this is the critical case. And this is the Ornstein-Zernike decay. And this m here to the d minus 3 over 2 is exactly capturing the behavior of what I called that constant c sub z before, as z approaches the critical value. Oh yeah, sorry, I wrote the wrong thing. You add these exponents here. Yeah, thank you for that correction. So the inverse of the mass is the correlation length. So we're comparing how big x is compared to the correlation length here. Yeah, which is the natural thing. So the mass is basically 1 over the correlation length. What's missing? Oh, yeah, sorry. Yeah. Thank you. All right. Now, let's talk about some applications. There are two applications I'd like to discuss. So the first one is random walk. So we'll have some one-step transition probability. D. It's a map from ZD to 0 infinity that sums up to 1 probability distribution. And I want it to decay exponentially. So it should be less than C e to the minus CX for some C's. Then the massive green function is S Z of X. It's the sum n equals 0 to infinity, Z to the n times the n-step transition probability, which is just the n-fold convolution of the one-step transition probability. So it would be D n-fold convolution at X. That's the green function, the massive green function. And it obeys, in the same way that we saw for simple random walk before, it obeys the OZ equation, the Ornstein-Zernike equation, that SZ is equal to delta 0 plus Z D star SZ. And I guess I want this to be symmetric so that S will be as required by assumption 1. And I want to argue that this obeys assumption 1 and assumption 2, and therefore we have our conclusion of the crossover theorem. So in order to look at assumption 1 there was that set omega, which will now be parameterized by Z, because we have a parameter Z that was not present previously, but now there is one. So it's the set of mu in RD such that the tilted chi Z is finite. So chi Z, remember, chi Z mu is just the sum over X of SZ of X times e to the mu dot X. Now this is going to be just equal to the set of mu in RD such that the tilted J, which in this case is D times S, D times Z, is less than 1. Okay, I think we had an equation somewhere over here that was in response to a previous question. It's this equation here. The J is just Z times D. Now let's define a set telegraphic Z to be the set of all Z in 0, 1, such that Z times D hat mu of 0 is equal to 1 for all mu in the boundary of omega. Okay, then theorem. Suppose that we have some subset of this Z. Basically, I want to avoid being too close to 0. So this Z naught is going to keep us away from Z equals 0. And suppose that there exists M, KIR, and zeta greater than 0, such that this Z d hat mu of 0, d hat mu is in this, no hat, yeah, Z d mu, the tilted Z, the tilted D times Z is in this Q M K I R zeta uniformly in Z in this good set of Zs, Z naught, and in mu. So let's suppose that holds. Then we're in the situation where we have the crossover theorem. So I claim that assumptions 1 and 2 are valid. I need to verify that for you, but once that verification is done, we get our conclusion, which is that S set of X is equal to C X eta X hat lambda X hat. And these things will also depend on Z. E to the minus mu X hat, which will depend on Z dot X times 1 plus the rho of 1. So we get the full crossover theorem, and this error is uniform. I mean, it depends only on M K I R zeta D and what is the choice of Z naught. If you take a worse Z naught, then you'll get a worse error. If you take Z naught bigger. We'll see why the Z naught is necessary when I verify the hypotheses. So in order to prove that, I need to verify assumptions 1 and 2. So let's do that. I think I'd like to do it just for the case of simple random walk, because it's very explicit. So let's do the proof for simple random walk. Verifying assumptions 1 and 2 in that case. So the D of X, I'm going to call P of X for simple random walk. It's 1 over 2D times the indicator that X is a neighbor of 0. S set of X is the sum over N of Z to the N n-fold convolution of P. And Z is in 0, 1. So here's a fact that's not hard to verify, but in the interest of time, I won't do it here. That you can compute this limit, this M of E1 exactly. You can just compute it. So it's the definition is the limit as n goes to infinity of minus the log of Sz of NE1 divided by n. I mean, I'll tell you what goes into the computation. It satisfies when you tilt P by ME1 E1, you should get 1. Okay, I mean, that's coming from the susceptibility being infinite. And so just solve that equation. And what you find is that the hyperbolic cosine of MZ E1 is equal to 1 plus D over Z, 1 minus Z. It's just an elementary calculation. There's a Simon-Leib argument that you can use that I'm not going to go into. Some of you know what that is. It implies that omega is open. It tells you that you cannot have a point on the boundary of omega where the tilted susceptibility is finite, because if you did, you'd be able to take a slightly bigger, there'd be a neighborhood of that point where it was. So you'd get outside of omega. So assumption 1 is satisfied. right? There wasn't much to assumption one. There was the symmetry assumption, which we have because P is symmetric. And then 0 is in omega, that's no problem. And omega is open, I'm saying here. What about assumption 2? So assumption 2 says that Z times, where's assumption 2? Here it is. It says that this tilted J, which in our case would be a tilted Z times P, is in this function space. So we need to verify the moment estimates. But actually the moment estimates, they really reduce for the case of nearest neighbor walk, because the nearest neighbor walk just requires, you know, the Y has to be 1 here when Q is Z times P. So it doesn't do anything. So these two conditions are exactly the same. Well, this one's actually a little stronger because it includes Y equals 0. And then there's also this condition. But again, you know, the Y is 1 because Q is supported on neighbors of the origin. So those moment estimates, they reduce. So it suffices. All you need to do is to check that JZ hat mu of 0, of Y summed over Y is less than or equal to M. That'll cover them all, actually, because the L1 norm is bigger than the L2 norm, or the D over 3 norm for that. If D is bigger than 3. So it suffices if this holds for all Z in Z naught, and for mu in omega Z bar. And this quantity here is just the same as Z D hat mu 0, or no hat. So that's a pretty explicit function whose norm we want to take. So by definition, the norm of this tilted J is just equal to the sum over Y in ZD of Z times P of Y times the hyperbolic cosine of mu dot Y. But Y has to be a neighbor of the origin, otherwise this P is equal to 0. So this is Z times the sum over neighbors of the origin. 1 over 2D, there's symmetry, so I'm just going to get 1 over D. And then I have the hyperbolic cosine of mu J. But this mu J is less than or equal to the MZ, right? We're inside of our omega bar, and each component, the L infinity norm is less than MZ. So this is less than or equal to the hyperbolic cosine of MZ E1. And so we just get Z times that hyperbolic cosine. But I think I just erased what that is. We know that the mass obeys the equation that the hyperbolic cosine is whatever it was. 1 plus D over Z times 1 minus Z. So this whole thing just becomes less than or equal to Z plus D times 1 minus Z, which is less than or equal to D. So that's the M, that's the capital M, it's just the dimension. How about the infrared bound? So I need to look at the real part of 1 minus Z D hat mu of 0 of K, and bound that below by a multiple of K squared uniformly in the Z's and the mu's. Okay, so this is the same as 1 minus Z D hat mu of 0. Plus the real part of, take the Z out, D hat mu of 0 minus D hat mu of K. I'm just adding and subtracting the thing at K equals 0. I know that this one is non-negative because the susceptibility is, I mean, that's a property of one of the conclusions of the proposition that follows from assumption 2. That the tilted J hat of 0 is less than or equal to 1 in omega bar. And as for this one, it's explicit. So this is greater than or equal to, and I guess D was P now, right? So these are all P's. So you write down what the real part is. It's going to, so the anti-symmetric parts are going to cancel. So you have Z, and what it turns out to be is the sum over Y and ZD of P of Y times the hyperbolic cosine of mu dot Y. And then we've got the Fourier transform part, which is this. And, you know, this thing here is greater than or equal to 1. We're looking for a lower bound. So I'll throw that away. And, you know, what are we looking at? We're looking at sum over J up 1 to D, 1 over D times 1 minus cosine of Kj, because P is supported on the neighbors of the origin. And this thing is bounded below by K squared over 2D, and there's this factor Z which is being carried along. And the reason that I introduced that calligraphic Z naught set was because this Z, when it gets close to 0, is spoiling the uniformity. But Z close to 0 is not what we're really interested in here. We're more interested in what happens when Z is near 1, so I don't feel bad about that. So the infrared bound holds uniformly in Z in Z naught 1 for any Z naught in 0, 1. So we just stay away from 0 to avoid the deterioration of the infrared bound. So KIR is equal to Z over 2D. Okay, so assumptions 1 and 2 are satisfied. So the crossover theorem holds. The conclusion of the crossover theorem holds in this case because the hypothesis does. And you can compute the norm explicitly. just using Lagrange multipliers. It's an elementary calculation. And so here's what the result is. I mean, you have a constrained optimization problem. You're trying to maximize mu dot x on the constraint that the j sums to 1. So the result is that xz, the z norm, this is not like an LP norm. This is the z norm that belongs to the particular value of z that you're looking at, is 1 over the mass, because that was a normalization that we installed in the norm in the first place. Sum j equals 1 up to d of xj times the inverse hyperbolic sine of uz of x times xj, where u is coming from the Lagrange multiplier. And it's the unique solution to this equation. 1 over d sum j equals 1 up to d of the square root of 1 plus uz of x, xj squared is equal to z. So you can plot this in my paper with Emmanuel Mishta, which is referenced in the abstract to these lectures. You can find plots of this norm as a function of z in dimensions 1 and 2. It's monotone in z. It varies between the L1 norm at z equals 0 and the L2 norm at z equals 1, the critical value. And in fact, I kind of alluded to this yesterday, but it's a general fact that under assumptions 1 and 2, that norm will always converge to the Euclidean norm when the mass goes to 0, provided you have uniform bounds, provided your j is in that Q space uniformly in the z values. These formulas, by the way, they showed up in the early years of work on the Ising model in the case of 2 dimensions. It wasn't noticed that it was defining a norm in that case, but these formulas are in the literature going back many years. So the last example that I want to talk about is example 2. So it's self-avoiding walk for a d greater than or equal to 4. A d strictly greater than 4. Let me say d greater than or equal to 5. It's a subtle distinction, but this is not weakly self-avoiding walk now, like I was talking about yesterday. This is really strictly self-avoiding walk. So I'm using much more than what we had yesterday. So it uses results of Hara and myself from 1992 and from Hara from 2008. And in particular, it uses the fact that the critical bubble diagram in dimensions 5 and higher, which I'm going to define without the contribution from x equals 0, is less than or equal to 0.493. Somebody asked me yesterday about what's the small parameter for the strictly self-avoiding walk, and I said it was 1 over d minus 4, which is not very small when d equals 4 or d equals 5, but there's a constant in front of that 1 over d minus 4. And the constant is basically this one, 0.493, which doesn't look very small, but it's small enough if you're willing to work hard enough to make analysis related to what I talked about yesterday go through. The technology was a little bit different then. It was all done in Fourier space rather than dealing with convolutions all the time. But it uses that, and it also uses the fact that the critical 2-point function is known to be bounded by some constant divided by x to the d minus 2. So we're bringing in some inputs that come from some fairly serious results. So now the convolution equation holds with Jz equal to z times p plus pi z. And the theorem is that for d greater than or equal to 2, Gz, so Gz is given by the solution to this equation. Pi z was that sum of diagrams. Gz obeys assumption 1. Okay, that's for every z. I won't talk about that. That's really elementary. And for d greater than or equal to 5, for every zeta, which is between 0 and 3/2 of d minus 4, there exists a delta, an m, and a KIR, such that Jz mu is in Q, the space Q, M, KIR, zeta, uniformly in Z close enough to ZC, and mu in omega Z bar closure. So as a corollary, that's assumption 2. So as a corollary, we get the crossover theorem for a self-avoiding walk for d greater than or equal to 5. Now the ingredients in the proof, there's a little bit more to it than there was for the case of the simple random walk that I discussed before. In order to control all of those diagrams, we need to know that we have to tilt pi. So that means we have to tilt the diagrams. So we're going to be bounding the diagrams with tilted lines as well. And we need to know that the tilted bubble remains small. So there's a bootstrap argument that where you vary mu rather than varying z like we did before, which tells you that if z is close enough to zc, then the tilted bubble is going to be close to this 0.493, which is going to allow all of the diagrams to be bounded. So the ingredients in the proof is there's a bootstrap argument. So it's varying mu. This was first done, I mean, this is standard now. I mean, it was done in 1990 by Hera, just for the case where mu was pointing in the E1 direction. And so all we need to do is to extend that to general directions. So it shows that the tilted bubble, B mu of x, which is the sum over x non-zero of gz mu of x squared, is close to B of ZC untilted if delta is small. That is, if Z is close enough to ZC, in which case the mass is going to be small, so mu is always going to be small, so we're not tilting by much in that case. And mu is in omega. So I won't go into that in detail. There's no time for that. But instead, let me just show you an example of how the norm estimate is verified. The fact that d is greater than or equal to 5 here means that we are in the domain where this norm estimate becomes relevant. And it's somewhat unusual in this business to be taking fractional norms, but that's what we needed in order to prove the non-centered Gaussian lemma, so we're stuck with that. It's only really relevant for d equals 5 in this case, because once d becomes greater than or equal to 6, the 2 always wins here. So let's just for the sake of simplicity talk about that case. So for the norm estimate, let's look at the case of the norm of y to the d minus 1, j, z, tilted y, 2. So let's take d greater than or equal to 6. We want to prove this norm estimate. Now the j has two parts to it. It has the nearest neighbor part. Where is it? It's maybe, here it is. It has the nearest neighbor part. That's not the part that we need to be concerned with here. It's really the pi. So I'm going to talk about the pi, and I'll just look at one diagram, which is the two-loop diagram, that sort of theta-shaped diagram, to give you a feel for what's involved. So let's consider what we usually call pi 2. We'll just consider this contribution to pi. So we're looking at the L2 norm of y to the d minus 1 times this diagram, tilted. Now, you remember that this diagram could be bounded by the third power of the two-point function. So there's some interactions inside pi, between these lines, but they're repulsive. If we ignore them, we get an upper bound. And so this is actually bounded above by the third power of gz of y. And what I'll do is write this as less than or equal to y to the d minus 2 times gz of y times y to the 1 times gz of y times gz mu of y. I'll finish in a minute or two. So that's the L2 norm that I want to take, but it's actually very easy to do this now, because we know that all the way up to the critical point, this, which is the biggest that this G can be, that it decays, it's bounded above by a multiple of 1 over y to the d minus 2, thanks to Takashi Hara's 2008 work. So we can just use L infinity norms on these first two terms, these first two factors. And they're just, these two guys are just bounded. Okay, because of this inequality. With plenty of room to spare in the second factor, by the way. There's only one power of y there. We could have had y to the d minus 2, and it still would have been fine. And this one is just controlled by the tilted bubble. So this is less than or equal to, 0.5 or something like that, a little bit bigger than 0.493. I mean, we have to be a bit careful about what that number is, but that's it. And so you just have to do this same kind of thing for the other diagrams, but there's very well-developed technology for bounding those diagrams inductively, like we talked about a little bit yesterday, and so it works. So I think that's all I wanted to say. So thank you very much for your attention. I'm happy to entertain any questions if you have any.
Any questions, either here or online? Silly question. Why is this double diagonal X not
Well, it's when you tilt the G. So if I sum this over X, let's just look at without the square. This is the same as the sum over X of GZ of X times the hyperbolic cosine. So this thing is greater than or equal to 1. So tilting makes it bigger.
I have a question as well.
Yeah.
So do you believe that the crossover phenomenon is true also for dimension 4? I mean, also for the critical dimension?
In dimension 4? So in dimension 4, we do know that for the continuous time weakly self-avoiding walk, so this is something that Bauerschmidt, Bridges, and I proved about 10 years ago, that the critical 2-point function has 1 over x squared decay, which is 1 over x to the d minus 4 with no log correction. So on the other hand, the mass does have a log in it. And our techniques, I believe, would not be sufficient to prove what is needed in order to carry out this program here. Do I think it's true? I'd probably, but yeah, probably true. The thing is that these m's will have logs in them. For lower dimensions, you know, this whole theory is built on a situation where the critical behavior is Gaussian, 1 over x to the d minus 2. And that won't be true in dimensions 2 and 3. So there's no hope there for this to work.
Questions? No, online there's no questions. Okay, so let's thank Gordon again.
Okay.